Welcome to The Explainer. Today, we're diving into a stunning scientific breakthrough that literally turns the chaotic, completely unpredictable power of electricity into something resembling lightning on rails. I mean, if you've ever looked at a messy tangle of power cords and just wished they could magically disappear, you are going to find today's topic absolutely fascinating. We're talking about a brand new way to control energy that honestly sounds like sheer science fiction, but it is happening right now in laboratories. So let's dive right in by asking the question that sparked a massive viral sensation back in early 2026. You might remember this. Social media was just flooded with rumors that we had finally figured out how to beam electricity through thin air, totally ditching wires for good. People were immediately hyping up the ghost of Nikola Tesla and dreaming of wireless power grids. But as focused learners, we always want to know what's actually happening behind those flashy headlines. Can we really just transmit electricity through thin air? Well, let's separate the viral myth from the lab reality here. The internet was convinced we'd soon have free wireless grid power beaming straight into our living rooms to run the TV and the fridge. But the reality? It's actually a much more precise and, frankly, much more fascinating laboratory triumph. What scientists actually pulled off is the ability to guide tiny electrical sparks through the air using sound waves. So no, we aren't wirelessly powering whole cities yet, but we are doing something that fundamentally rewrites our understanding of how electricity can be controlled.
All right, let's jump into Section 1. Meet the acoustic wire.
So, what exactly is an acoustic wire? Basically, it's an invisible path created in the air using high-intensity ultrasonic sound waves to precisely guide electrical energy. It's the brainchild of an incredible collaboration between researchers from the University of Helsinki in Finland, the Public University of Navarre in Spain, and the University of Waterloo in Canada. By using ultrasound, this team effectively tamed the wild branching nature of a spark, giving it an invisible, perfectly controlled track to follow. In this mind-bending research was recently published in the highly esteemed journal Science Advances, under the title Electric Plasma Guided with Ultrasonic Fields. This wasn't just some theoretical paper either. It was a physical, undeniable demonstration proving that power absolutely does not always need solid cables to travel safely and predictably. They literally manipulated the air itself to act as the conductor.
The lead researcher on this project, Dr. Asier Marzo from the Public University of Navarre, hit the nail on the head when describing the wonder of this accidental discovery. He noted that they actually observed the phenomenon over a year prior, and it took them months just to figure out how to control it, even longer to decode the actual physics behind why it was happening. They knew the ultrasound was guiding the spark, for sure, but the underlying mechanism was this massive mystery they had to solve together.
Moving right along to Section 2. How sound guides sparks.
So, how's it done? The researchers uncovered this perfect continuous cause and effect loop. First, an initial electric spark passes through the air, heating up a tiny localized region. Because it's hot, that air expands and its density drops. Right? Then, and this is where the magic happens, the high-intensity ultrasound waves physically push this lighter, low-density air into specific regions where the sound intensity is higher. Finally, the next electrical spark just naturally follows this exact channel of lighter air because it has a lower breakdown voltage. The sound waves are essentially carving a path of least resistance right out of thin air.
Now you might be wondering, haven't we tried guiding sparks before? We have. But the old method was, well, highly problematic. Scientists used to use things called electrolasers, which required dangerous lasers and insanely precise timing. But this new ultrasonic method? It's a total game changer. It is safe for human eyes and skin, the equipment is super compact and affordable, and you can run it continuously without the risk of frying your lab equipment, or, the scientists themselves.
Which brings us to Section 3, the 4-centimeter reality.
Okay, before we throw out all our charging cables, we do need to ground our expectations just a bit. The crucial point here is that this incredible lightning on rails is currently only about 4 centimeters long. To put that into perspective, that's roughly the length of a standard matchstick. These experiments weren't built to deliver usable power for charging a laptop. They were proofs of concept focused purely on controlling plasma over very short distances.
But please, do not let that 4-centimeter limit sound like a disappointment to you. It is actually a massive microscale triumph. Within that tiny distance, the research team achieved unprecedented control. They successfully curved the electrical paths right around physical obstacles. They were even able to selectively light up individual neon bulbs without the electricity jumping unpredictably to other metallic objects nearby. Achieving that level of control in open space, it's almost unheard of. And as Professor Ari Salmi from the University of Helsinki points out, it is exactly this precise control that makes the discoveries so vital. This millimeter precision is what pivots the whole thing from a neat laboratory party trick into a genuinely revolutionary tool. Because ultimately, it's not about how far the power travels, it's about dictating exactly where it goes.
And that leads us perfectly into Section 4, Future Magic, Contactless Braille.
Because this energy is so perfectly guided by sound, scientists are already exploring a wild list of uses. We're talking atmospheric research. In biology, imagine patterning bacteria in a petri dish without ever physically touching the sample. In electronics, it could allow for the selective activation of microscopic circuits. But the most exciting potential of all, at least in my opinion, lies in contactless tactile interfaces. First author Josu Irisari envisions using these controlled, very faint sparks to create haptic feedback right on the skin. Since they can guide the spark exactly where they want without any mechanical movement, they could create highly specific tactile stimuli on a person's hand. This brilliantly illustrates the potential for the world's first true contactless Braille system. Or think about incredibly immersive haptic feedback for spatial computing and VR, where you are literally feeling the digital world through guided acoustic sparks.
So it leaves us with a deeply fascinating final thought to chew on. We might not be wirelessly powering our massive cities tomorrow, but we are absolutely on the verge of interacting with energy in ways we never even thought possible. What will human interaction, communication, and technology look like when electricity and touch can flow safely without wires, guided through the air by nothing but invisible acoustic rails? It's pretty wild to think about. I hope this explainer shed some light on this incredible breakthrough for you. Keep learning, keep questioning, and I'll catch you in the next one.